So hi, I'm Ben Hamill, my Twitter website and my email address. I work at a company called ReturnPath. We're the global leader in email intelligence, which is kind of a mouthful, but suffice it to say we spend a lot of time trying to make email more awesome. And specifically, I work on a product called Context.io, which is an HTTP API for email. You may have talked to Tony at our sponsor booth. And I just want to drop in here, we're hiring. If you want to talk to me about that after this or talk to Tony, I would be happy. So I want to tell you a story today about my first foray into thinking about measuring and doing anything about performance in Ruby and like the user's experience with performance. Before this, the project that I'm going to tell you about, I was kind of intimidated about it, and it wasn't as bad as I thought, so I hope to convey that not as bad feeling to all of you. So we're going to talk about three things. First, I'm going to talk about sort of the state of the code base when I started. Then I'm going to tell you how some tricks that I discovered to sort of fake out speed and not actually make it any faster. And then we'll talk about achieving real speed. So the API mentioned in the previous slide will remain anonymous throughout this presentation, partly because I want to protect the identity of the innocent. It's not my API that's slow, but also because it has to do with a project that we're not ready to announce yet. But we will say some things about the API which must not be named. First of all, it's all XML all the time, which is super awesome. So you're making HTTP requests at this thing with XML bodies and getting back responses with XML in them. And there are two kinds of entities that the external API knows about. There are documents, which have like a body largely of text, and then a set of changes. And the changes are like add, delete, modify. So when someone moves a document to a new folder, you get a change. When they receive a new document in their account, that's add. And if they delete a document, that's a delete, clearly. So the change document is very data light, though. And if you want to know details, you have to fetch the document itself. So the way that my app works, we perform what we call sync, which is to say we synchronize our understanding of the account in foreign API with what is true on their server. So the cloud is their API, right? So we make a request and we get this change document down. And then for a given line or a given command in the change document, we fetch the body of the message, do some analysis on it, and we do that for every line in the change document for however many there are. And then once we've done that, we can like mark the stamp, the timestamp, and do some post-processing and be done with our sync. So here's where we would come to sort of the problem, right? So the syncs that I do is storing this data. Then there's an iPhone app that a team member is working on that uses this data. When a new user downloads the app and signs up for it, it triggers a sync and then polls for the post-processing results. And when it finds something interesting, it like updates to show the user the interesting thing. And interesting here is like determined by a Bayesian classifier, but it's sort of beside the point for our purposes. Just know that it takes a little time after the sync is done to determine whether something was interesting. And the problem was that the time between finishing sign up and step 3 was too long. And I don't know about you guys, but when I'm trying out a new iPhone app, I'm like, oh, what does this thing do? You know, I'll click on the thing, sure, you know, here's my credentials, and I'm looking at a spinner now, and if it takes longer than about 5 seconds to go from this to this, and this is the face of like bad user experience, yeah? So we're going to avoid like rage uninstall and screaming babies, and you know, achieve that better user experience. So the first question to ask is what is actually slow? Like we know the whole thing is slow, but what's the slow part? And we had an intuition that it was something external, because of course, like my code's not slow, right? You've never written slow code in your life. But your intuition can be wrong, and it would be abysmal to guess what is slow, spend a week refactoring it, optimizing it, deploy it, and then have zero impact on how fast your thing actually runs. So you have to measure things to actually answer this question. So this was our intuition with some other external stuff that we're using, who being the API that's not to be named. But you could be using too much RAM that's bogging down the system, or pegging your processor, etc. So learned about some tools to find out. The first of which is called top. It's a command line tool from Linux, and this output is actually taken from my laptop while I was making the slide, because I didn't capture it while I was actually running it. So I deployed to my sync process to an alpha server, went on there and ran top. This is kind of a lot of output, so I'm going to highlight the sort of major important things. So this bit here, this whole line is in kilobytes of memory, and so this number here is the amount of free memory you have. If it is low, you're using a lot of RAM, and if it is high, you're not. In our case, this number was plenty high. So, okay, we're not RAM bound. That's good news, I guess. The next important thing that I want to draw your attention to here is this column. So each of these lines is a process running on the machine, and like one of these lines will be your process that represents the code you wrote, or in my case, the code I wrote. And this line is the percent CPU that it's using. It will total 100% times the number of cores in the machine. So if you have 4 cores, it might total 400%, assuming you're pegging the whole thing. It's more common that it will be, like one process will be pegging one of your physical cores, and other things are still getting scheduled because you have other processors available. But again, in our case, these numbers were relatively low. Like, I could see my Ruby process on there taking up some resources, but it was not an unreasonable amount, so that wasn't the bottleneck. Okay, so that's top in a nutshell. The next tool I learned about is IOStat. You can read this perfectly, right? It's good. So IOStat has kind of a lot of output, and I put this here because I'm going to refer to the general shape of it, but we're going to zoom in here on the command. The first business here is just my prompt. So the command is IOStat, and then I fed it the options X and K. X is for extra columns, and the K is to put things in kilobytes per second, because it's easier to understand as a human. Then you feed it 2 arguments. The first is the number of seconds per bucket, and the second is the number of buckets. And the general shape of the output above, right? Each grouping of lines is a bucket. So it shows you the data, it waits 5 seconds, and then it shows you the data from that 5 seconds, and it waits, and it shows you the third bucket. What it's showing you data about is the amount of disk reads and writes that your system is doing. So you can use it to measure how waiting on I/O your program is. So this is the first thing to look at here, and I've tried to zoom in. So this percent util here goes up to 100, and if it's 100, you're spending a lot of time waiting on disk read and write. And if it is below 1, like here, you're not spending very much time. So these 2 tools can help you confirm or eliminate RAM, CPU usage, and disk reads and writes. In our case, none of those were the options. So I was beginning to suspect, something on the network, something across the network was slowing me down. So I turned to a third tool called perftools.rb. It's a Ruby gem, and it's like a re-implementation of a C tool called ProofTools. So this example code is stolen pretty much right from the README, and I did effectively this. I went on to the alpha server, I opened up my init script, and I required the gem. You start the CPU profiler and feed it a file to write to, do whatever your work is, and then you tell the profiler to stop, and it like closes the file. In my case, I actually put the stop in another thread that waited 5 minutes and then stopped, so I get a 5-minute sample without knocking over the whole process. After you've collected all the data, you can generate output. This output actually is from the alpha server. While I was doing the project, I saved to put in a comment in a ticket. So you run pprof text and you feed it your what's taking so long file. And then this column. So the way that the tool works is at regular intervals, it asks the Ruby VM, what method are you running, man? And it just keeps a list and like how many times the responses were which methods. So then when you run pprof, you can use it to generate different kinds of output, but the text was sufficient for my case. It basically just aggregates it up and tells you. So this column is the percentage of times that a given method was the answer to what are you doing right now. So the first line you can see is IO select, which I'll tell in a second. Then there's TCP socket initialize and IO write. All of this is like network related stuff. In particular, IO select, which is 71.6% of the time. That's like not quite 3/4. That's kind of absurd, right? IO select was basically my sync process, waiting to hear back from an HTTP request. So that's spectacular. We're not actually doing processing that's taking the time. We're just waiting to hear back from somebody else. So I did a little bit of further investigation, like cutting pieces of the code base out and doing external calls. And what I determined was that a round trip to fetch the body of a document took about half a second. And at the number of documents that we were generally working with, at least that we were testing with, it ended up being a lot of seconds all added up that we were just spending like hanging out. And that was by far the slowest external call we were making. So, wait. So we've been talking about the application's performance, and I had sunk about 3 days into it at this juncture, and I kind of was like wanting to think about my performance because, of course, like developer time is valuable, and there's an opportunity cost. When you choose to do one thing, you're not doing something else. And I like heard about these things called threads, and that like you could do stuff in parallel and it would be faster, but I didn't know anything about it. So it was like maybe it would take like a week to do like learn and then do something with it. But I kind of wondered if there's something that I could do today, you know, that would be maybe good enough, you know? So I kind of took a step back and started thinking, what is actually important here? You know, a user doesn't know when a sync started and when it ended. A user doesn't even know what the hell a sync is. They know they press the button and then they're looking at a spinner, which sort of implies the answer to this question. Like what actually matters is that the app gives feedback to the user. If they're looking at something that doesn't appear to be doing anything, they feel like it is slow. But if it changes in some way, they feel like it's working, right? So I started to look for ways that I could make users feel like the app was this, even if the app was actually like this. So I devised 3 simple strategies to sort of fake out speed to like give users feedback earlier. So the change document, when it comes down, the like list of commands to do, comes down in chronological order. But people in general, in our case specifically, today and yesterday is way more interesting than 3 weeks ago and last month. So we were parsing this XML document and sticking it in array. I literally just added .reverse, small change. And it just put the more interesting stuff to be processed first in the huge list. I also then like realized there are 3 kinds of changes, but in the case of a delete, that document's not there. There's no reason to spend half a second to get a 404, so don't make a call. And updates are metadata only. Like if you move from one folder to another, that's reflected in the update command, so you don't need to fetch the document's body. No reason to spend half a second. Only add do we actually need the document body so that we can send it to the Bayesian classifier to find out if it's interesting? So that's like 2 out of 3 cases that I don't even have to make the call. It's not doing work faster, it's just doing less of it. And then the third is persistent HTTP connections. So I was using Faraday, which is a gem that presents a uniform API for dealing with HTTP requests, and then you can switch out the sort of back end of it, they call it an adapter, for how it actually makes those. So out of the box, it uses NetHTTP from the standard library. And I already had a Faraday config block that was doing other configuration. So I installed the gem NetHTTP persistent, added the one line, and it uses it. What the NetHTTP persistent does is when you make a request to a host, it holds on to that connection for a little while so that if you make a request to the same host, it reuses the connection. So it saves on setup and teardown time and just kind of handles it for you. So, my 3 simple hacks, or fixes, I should say. This is the time for various benchmarks before I made my 3 changes. And the way that I got this is I sat down next to the iOS developer and he ran the app in the test thing on his computer, and I sat with my phone and like hit the stopwatch. So it's super scientific, but so feedback is the time from like finishing sign up to having the app show some change. The total sync time is like the time that this my sync process had seen the last document, and then you can see 3 minutes later, that's the last time that the Bayesian like the time at which the Bayesian classifier had seen the last message. So I made the 3 changes, and the times went like this. The like 15 minutes to 2.5 minutes, I felt so good. I was like, I am the best programmer. I'm pretty sure that's all NetHTTP persistent. Maybe not all, but largely. So I felt really good about this. Like I cut the feedback time in half. I was like, awesome. So I took it to the product owner and I was like, look, it's like twice as fast now. It's way better, and it only took a day. It didn't take that week I was talking about, you know. And he was like, that's really great, Ben, but that's like half a minute. And like, I don't stare at my phone for half a minute, right? So it's better, but it's still not good enough. So cool, we shipped that. But then I went back to the drawing board and started to learn about actual speed. So now we're going to talk about threads. And before we talk about threads, I need to talk about something called the global interpreter lock, or the GIL. So in Ruby, if you have 2 threads which need the interpreter to execute whatever they're doing, and one of them will have the attention of the interpreter, sort of, to be doing its stuff, and it has a global lock. So your other thread has to wait until it is done with the interpreter, then it can run. The like practical fallout is if you have something that takes a minute and you want to do it 10 times, doing it in a row takes 10 minutes, you might think, oh, I'll do 10 threads, I'll do it all in parallel, and it will take 1 minute. But if what you're doing needs the interpreter, it means that one thread will have the lock and do whatever it's going to do, and then it's done, and it will unlock, and somebody else will grab it, and it will do, and then unlock. So you have 10 threads, but you still end up running your 10 things in sequence, and it still takes 10 minutes. But note, I said if it needs the attention of the interpreter to do whatever it's doing, which kind of implies that some stuff doesn't need the interpreter. So what's parallel, what's not? Things that are not parallel, which need the interpreter, is like mucking around with things in memory, like reversing an array, or doing math, or most methods that you will call on most objects that you run into. But things that are parallel are basically anything that needs, or that will use a system call. So if you read from a file, system call. If you sleep for 10 seconds, system call. Notably for me, if you do io.select, system call, because it's using the system to talk to the networking hardware, which is talking to the whatever. So for our case, because we had identified that as the bottleneck, CRuby's threads were actually really great way to get some speed. Note, this is a C Ruby specific JRuby, and other implementations have different parallelization stories. So, okay, if you're going to do threading, though, you have to manage them. So part of the reason why those 3 changes were so easy is because they were really low footprint. But when you start managing threads, you're necessarily introducing more more lines of code. So in my thinking, there's basically 2 ways to manage threads. When you're dealing with a group of threads, you generally call them a pool. So there are temporary thread pools and say persistent thread pools. So this is kind of an example implementation of a temporary thread pool. If you imagine like work items is an array of, say, add commands or something in my example, and whenever you want to process them, you call do work and you feed in the array, right? So with a temporary thread pool, you would create an empty array for each work item. You spin up a new thread that's going to process it, whatever that means for your business. And then the next to last line there, you can see I'm doing this pool.each join business. So when thread A calls join on thread B, it means that thread A will wait for thread B to be done before it continues. So in this case, the thread that is executing this method will wait for all the threads that it just spun up to finish before this method returns, before do work returns, right? So it means that every time we have a group of work items that we want to deal with, we're spinning up a bunch of threads, waiting for the finish, and spinning them down. And then we have more stuff to do. We spin up a bunch of threads, and we spin them down, which is great because like the bookkeeping is super easy. You don't have to like manage them really. But there's some overhead with spinning up threads and tearing them down. And also, for our case specifically, when NetHTTP persistent keeps its handle on a connection, it does it on a thread-by-thread basis. So if we were spinning up threads and spinning them down, we'd be completely throwing away all the benefit we got from holding onto those connections. So persistent thread pools. The downside of persistent thread pool is that you have to manage it a lot more. The upside is the thread pool hangs out and you send stuff to it and it stays for the life of the Ruby process. So there's going to be several slides of code here, and I will walk through them. So the first few lines here, we're sticking Q objects into some global variables. That's basically a shortcut for like the sake of concise examples on the slides. But they need to be available to both the threads that are doing the work and the thread that is giving work to those threads. So this was a reasonable shortcut. Q, you can think of sort of like an array, except it's all push and pop. And the reason that you use it when you're dealing with threads is that the pushes and pops are atomic. So if 2 threads are trying to pop from the same queue, they will not run into each other and like pop the same value. One will win and get a thing, and the other one will lose and get the next thing. This is really important so that you can avoid like race conditions. So okay, well there are 2 queues. Oh, these are going to be like the input and output to our work threads, right? Items go in, and whatever the results are come out. And then, so then 100 times, I'm going to spin up a thread and put it in this array. The 100 there happen to be, so I had to do some experimentation with my code to find the right number of threads to spin up. There's basically, you will find a point, most likely, where adding more threads does not add more performance. And so you will want, like if you were doing this, to experiment to find what that is for the environment you're deploying to. So anyway, 100 times we'll spin up a thread, and then in the thread call worker.workloop. We'll look at that implementation in a second. So that basically sets up our thread pool, which knows how to process our work. Then do work will pass our work items in, and the idea here is we can call do work with more work items as many times as we want there, probably in a loop. In our case, we were pulling the work from like a remote queuing system. And it will reuse the same 100 threads. And then I have commented out pool.each join here because the whole idea here is that this thread pool is alive for the life of the Ruby process. So you don't need to have this thread wait and join all those threads. Like, you want those threads there until Ruby quits, and when Ruby's quitting, like, it'll manage this all on its own. So let's look at work loop. This is sort of the complicatedness. So this is the bookkeeping complicatedness. Go back. Yeah. So here's the work loop, which is actually 2 slides here. But so the real, like, the actual work part, as it were, is the loop line inside the loop. So we call this method, it basically a loop, and it's looking for work items on work items in, popping them off, passing the process. Whatever that returns, it's pushing them into the results queue. So that's what I meant earlier when I said that they were like the input and output to our work queues. So that, like, that's how these threads actually do the work. The rest of this is sort of bookkeepiness. So when you try to pop from a queue and there's nothing in it, it raises thread error. It's not like thread : queue empty error or anything helpful like that. It's just thread error. So you basically have to plan for this eventuality unless you can guarantee that there's always something in your queue. In our case, this was expected because the worker may or may not have a sync at any given instant. And we just went into, like, oh, if there's nothing in the queue, cool, look again. So we just retry there. It goes back to the top of the work loop method, enters the loop, and tries to pop again. That's like exceptions is flow control, but that's the way queue is implemented, and it's something you just kind of have to deal with. So the other thing, that's my slide transition to scroll down. The other thing is, because we want these threads to be alive as long as the Ruby process, they need to be bulletproof. So here I'm rescuing standard error, because if anything goes wrong when I'm trying to process the whatever, I want to log it, I want to know about it, but I don't want that exception to kill this thread. So I log it, and in this case I'm sticking the symbol error in the results queue so that I communicate something went wrong, and then retry. Note, retry does not mean retry the work that just raised an exception. That work just got dropped on the floor because this is kind of a naive implementation. In our case, that was fine. In many cases, you will want to do something about that more. You may need to store it and retry it again in 5 minutes or whatever. So retry just goes back to the top of this method and starts the loop again, probably to pop another work item and actually process it. So let's go back to the code that called this, right? So all that stuff we just talked about is happening in each of our 100 threads. But there's still nothing in the work items queue. So at this point, when Ruby's executing all these lines, there's 100 threads that are going pop, nothing, pop, nothing, pop, nothing. Then we hit do work. So last time, do work was the whole thing with our temporary thread pool. Now do work is pretty simple. So we pass in our array of stuff, we iterate, and each one, we just put it in the work items in queue, and it will get handled by our persistent pool. And then I have a cop-out comment, do something interesting with work item results. So in our case, I needed to know that all the items I had queued to be worked on had finished. So I counted the items as I put them in, and then I counted the items as they came out. And when those numbers were the same, I could mark the timestamp and trigger some post-processing stuff. So that was why it was important for me to stick this error symbol in the case of an exception, so that there would be an item to count instead of having this just wait on stuff that was never going to return. So, not what I'm going to do. Go forward. Okay, so everybody's remember this slide? So these are the times after my 3 simple changes. Then I took it ended up being about a week to learn about threads and implement persistent thread pooling. And the times did this. So like 2.5 went to a minute. I felt really good about that. 17 seconds is still kind of long in like looking at your phone time, but it's important to remember when you're doing performance stuff, like there's almost always something you can do to make your code faster, but you got to stop somewhere. So you have to make a determination of what is fast enough. And our determination was for the time investment, this was fast enough for now. And if we have some other priority stuff that we need to get to, and we may circle back and try to make it even faster. Like we have some other ideas to try. So yeah, 1 minute to 17 seconds. Felt good about that. So I've kind of hit a lot all at once. So let's kind of go back and review, and then we'll do questions. So first step, you're worried about performance, something takes too long. First is to figure out what is actually taking too long. And top, IOStat, perftools.rb are your friends for that. The second question to ask is, can I pretend? Can you give the user feedback earlier, or like in our case, reverse sort something? Can you distract the user? So like people talk about putting mirrors in elevator lobbies, and even though the elevator does not come faster, people feel like it doesn't take as long. So like if you show the user a tutorial while they're waiting, they're not like just waiting, they're learning, right? Then, if that's not going to cut it, you can go to threads. Remember, in MLI, you have to deal with the global interpreter lock, which means you can parallelize I/O well and other things not at all. And when you're managing your threads, thread pools, there's 2 kinds, temporary and persistent. So I'm Ben Hamill, and I'll take questions.